Today I want to talk about permutations, but with a significant amount of restrictions on how many options are available in each position. And with the overriding idea that we have to promise and calculate these specific restrictions first. It's the bedmass of counting methods. Let me pick a nice little word here. Let's just do something school related. And so here are the letters that I am selecting from. This is a nice little sample space. Sometimes when you're given a word like this, a sample space, 1, 2, 3, 4, 5, 6, 7, there's 7 things. I like reorganizing them. A lot of these questions about letters are going to ask you to put vowels first, consonants first. And if it helps, if especially if English is not your first language, it might be kind of important just to make sure that you have maybe grouped some of the consonants together, the ones that are hard letters, p and m, and some of these soft vowels are now together, just as a nice little visual aid, because it's nice to keep track and make as little mistakes as possible. Now, if I asked, how many arrangements are possible, let me just move that a little bit. How many arrangements are possible if I have to begin with a vowel? We would want to kind of take account of this and how many arrangements are possible of all 7 of these letters. And the strategy that I really do focus on here is the fundamental counting principle. Counting principle is a way of asking every single time, in this context, how many options are there available here? How many letters are available? And because there's a restriction, I can't say that there's 7 letters available for that spot. There are not 7 vowels available for that spot. And this is the restriction of the question, with a very, very specific request of, hey, it's got to begin with a vowel. As long as it begins with a vowel, we're okay. These other kind of wide open spaces, these are, this is what I would call unrestricted. Totally wide open, nothing really promised for any spot, anything left. But when I look at what's available here from the vowels, I do say that there are 3 vowels currently available. Now, we're not selecting all 3. I mean, we're not just saying now all 3 have been selected. We're saying that there is 3 different possibilities. In the land of probability, I would say immediately there would be a 1 in 3 chance of guessing someone's password if you knew it started with a vowel. And currently, even just picking that one letter, there's a 1 in 3 chance of getting that right, because you're only selecting one out of the total number of options for that spot alone. And so the number that you're selecting, the number that would be correct, 1 in 3. So now that we have picked, and one of the things about arrangements, as we should know, is that we don't get to use the same letters over and over. We're simply shuffling them around. We're simply moving them. And so while one of these vowels has now been picked, I definitely don't have 7 left. I have only 6 left. I have 6 letters left. Count them: 1, 2, 3, 4, 5, 6. Because there is no rule on that second spot. Anything is fine. As long as the start was a vowel, anything left was cool for that next spot. And then 1 more is gone, down to 5. 1 more is gone, down to 4. Unrestricted space is where you would see those countdowns, those very common permutation countdowns. And we get this long string of numbers, and we always multiply in this case. It's because we're picking a letter and then another letter, and then another letter, and we could multiply through. And in another notation, we could say that this was 3. There's no symbol for that 3 for this in the factorial notation, where the only countdown really worth writing in notation was the 6, 5, 4, 3, 2, 1, 6 factorial. And or if you want to use even a more fancy notation, you would switch this into permutation notation for each of these stages, where there was 3 vowels available. We only picked one of them. That's the same as the restriction. It's equal to 3. And then there was 6 things left. And we did arrange all 6 of them. And you don't need to know those notations in 30-2. The counting principle for me is the easily arguable the best strategy to really show the work, really think it through carefully. But in either case, we should have eventually ended up with the total number of ways that we could begin with a vowel. Let's just do one more in this context, beginning with a vowel. Let's switch it up, and let's say that it has to begin with exactly 2 consonants. Now, there's several restrictions kind of buried in that statement. As I go to set up my fundamental counting principle, 1, 2, 3, 4, 5, 6, 7, I am absolutely concerned about what's going to show up in the first spot and the second spot and the third spot. It's not until the 4th letter that I can kind of let my guard down and say, well, whatever's left at that point will be completely ruleless, unlawless, unrestricted. But I very much have 3 important things to talk about at the beginning. Let me just get my sample space ready to go. Diploma. Here are my 7 letters, nicely organized. Beginning with exactly 2 consonant means this is a consonant, this is a consonant, and this is unbelievably not going to be a consonant. You cannot allow the third consonant to show up, meaning basically it's a vowel, since there's no other choices. And let's keep track. There are currently 4 consonants, 1 in 4 chance of picking it. Boom, one of them's gone. There are still 3 consonants left. Boom. One more consonant down. There is still 3 vowels left. So we haven't even touched those yet. As long as it wasn't one of that L or M, there was 3 good choices for that next letter. Boom. One of those consonants, or one of those vowels, has now been selected. And now for those 4 available spaces, coincidentally, 4 available options. Now that we've thrown out all these silly rules out the door, anything goes, totally the Wild West now of current counting methods. And we get this very nice countdown, where the only notable countdown was when the restrictions ended, and we get that 4 factorial at the end, where there was, let me grab some color, but this is still just whole numbers. 4 times 3 was the consonant, almost a full countdown, but not quite. There was 3 vowels, no countdown there, no need to use a factorial, but 4 times 3 times 3 times 4 factorial does eventually give me a total answer of 864 for that very specific question type and restrictions. We can do the exact same setup, all the same ideas, but I do just want to kind of talk about a number problem. And so here's my new sample space. Let me just call this example 2. And a sample space could be built out of some digits. 0, 2, 3, 5, 8, 9. There are 6 different digits to pick from. And I'm going to, just kind of say this is an arrangement set up. And what I really mean by that is that there are no repeats allowed. Once you use the 5, you can't use that 5 again. You get one shot at that 5 if you need to. And we're going to build some natural numbers. And what we mean by numbers, which is totally different than, say, building a code, is that this would not really be an efficient or sensible way to start a number. That carries no weight, it carries no value. And so immediately 0 is not really an acceptable digit at the start of a number. You put it in second or third spot, you better believe that that's going to be building a really, really good number. 0 carries a purpose and value when it's in the middle or at the end of a number. So we got to really be careful with this. And so I'll just kind of build one example here. We're looking to use all 6. I'm looking to build even numbers, natural arrangement, no repeats allowed. So I've got a couple of rules to play with here. 1, 2, 3, 4, 5, 6. I immediately have a little bit of an issue at the start because it can't be a 0. But my main issue here is that I have to make sure it is an even number that eventually gets built. The only digit that makes something odd or even is the last digit of any number. And so I have my restrictions. And I do need to start at the end and promise all of the even numbers to that spot. Oh, I don't like this. Sorry. We're going to do odd. For reasons I won't get into, I almost kind of set myself up for a bad time. We're going to do odd. Sorry about that. Same thing. Odd number at the end. We're going to use all the digits. Now, looking through my numbers here, 1, 2, there's 3. 3 of these numbers are odd. That means I don't have 6 options here. I have 3 options here. Gotta start at the end. Gotta make sure you've promised it. It would be a bad choice to kind of run out of odd numbers by the time you get to the end of this digit. There are 3 odd numbers to pick from. Only one of them is being selected. One of them can take the sacrifice and hold that spot while we go now arrange all the other digits. Now, given that 0 is a non-cool number, it is not an acceptable way to start this spot. I am limiting down to only 4 quality choices left. One of them has to be selected to hold that position. Now we can move on to arranging. Now, whatever's left is going to work. 0 is back in the game. Everything that hasn't been crossed off is available. And that's 1, 2, 3, 4, then 3, then 2, and then maybe the last digit. This is not a repeat just because it says 4, 4 or 3, 3. That's not a repeat. That was just how many options were available at that moment. And then later on, there happened to be 4 options available later in the arrangement. It's just a little bit of a coincidence that there was 4 options. And this happens because of these restrictions. I mean, when we're only saying 3 numbers are allowed to be here, but there was a 6 in total, eventually there's only going to be 3 options left once we start arranging those other things. This isn't an actual number that we've just built. This is just a fundamental counting principle telling us all the options multiplied by all of the options, which is a way of saving us a whole bunch of time because I really didn't want to say that there was 4 options for the first number and then 4 options for the second number. and then three options for the next number, and then somehow create this gigantic tree diagram which would show all of the multiplications and all of the things. We're just trying to show how many options times how many options times how many options, and that was the best I could do given how many digits there were. And so 4 times 4 times 3 times 2 times 1 times 3 gives me 288 as the number of 6-digit numbers that couldn't start with a 0. The last digit had to be odd. And that makes for a quite formidable question in counting methods.